All right, if you're deep into studying for a chemistry final, you have landed in exactly the right spot. Today, we're going to trace the entire life story of iron. I mean, from a plain old rock through the insane heat of a blast furnace to its powerful life as steel and then its inevitable return to the earth as rust. Let's get you acing that exam. So, take a look at this. How in the world does this reddish rock become this, the steel I-beam holding up our entire world? It's kind of crazy to think they're fundamentally the same element, just at very different stages of their life. The big question we're tackling today is what is the incredible chemical journey that makes a transformation like this even possible? So here's our game plan. We'll start with iron ore, how we find it. Then we're going to dive right into the heart of the blast furnace. After that, we'll see how raw iron gets its superhero upgrade to become steel. We'll also cover its inescapable fate, rusting, and then wrap it all up with a lightning round review of the 5 key concepts you absolutely have to know for your exam. Okay, let's start at the very beginning, down in the Earth's crust. Before we can even think about making steel, we've got to find the iron. And here's the thing about iron. In nature, it's pretty reactive. It really doesn't like to be alone. You'll almost always find it chemically locked up with other elements in compounds that we call ores. Now, iron ore comes in a bunch of different forms. You've got your oxides, your carbonates, even sulfides like iron pyrite, fool's gold. But for making stuff on an industrial scale, the undisputed king is hematite, Fe2O3. This reddish-brown rock is the main ingredient for pretty much all the steel in the world. If you remember one name, make it hematite. So, once we've dug up all this ore, we can't just toss it into a furnace. It needs to be prepped first. Step 1 is called concentration. Basically, we crush it all up and use techniques like magnetic separation to get rid of all the useless rock. Then comes step 2, roasting. We heat it up in a massive oven with hot air blasting through it. This does a couple of things. It burns off nasty impurities like sulfur, and, this is really important, it converts any other iron compounds into that perfect Fe2O3 we need for the next stage. Okay, the ore is prepped and ready to go. Now for the main event. We are heading into the chemical reactor that basically built the modern world, the blast furnace. This is where the real transformation begins. Just look at this thing. Think of it as a giant chemical skyscraper. At the very top, we feed it a very specific diet of 3 key ingredients: our iron ore, something called coke, which is pretty much pure carbon, and limestone. As this whole mix slowly sinks down, it gets hotter and hotter, and a bunch of critical reactions happen in different zones. Let's break it down, starting from the very bottom and working our way up. Right at the bottom, in the zone of combustion, it is unbelievably hot. We're talking up to 1700 degrees Celsius. Hot air gets blasted in, and that coke burns like crazy, first forming carbon dioxide. But, and this is the key, that CO2 immediately reacts with even more hot coke to become carbon monoxide, or CO. This is the most important step. We've just turned solid carbon into a gas that can go and do the real work. This CO gas, it's the true hero of our story. Moving a little further up the furnace, we hit the zone of slag formation. Remember that limestone we added at the top? Well, the heat here breaks it down into calcium oxide, which acts just like a chemical sponge. Its job is to grab onto the main impurity we have left in our ore, which is basically sand, or silicon dioxide, and it reacts to form a molten liquid called slag. And because this slag is less dense than iron, it just floats right on top, which makes it super easy to skim off and get rid of. And now for the grand finale, inside the furnace. As our hero, that carbon monoxide gas, rises up, it passes through the iron ore in the cooler upper region, the zone of reduction. This is where it does its main job. The CO literally rips the oxygen atoms away from the hematite. And what's left behind? Pure molten iron, which then drips all the way down to the bottom to be collected. We did it! We have molten iron. But hey, the story is not over, not by a long shot. The raw iron that pours out of the blast furnace is called pig iron, and honestly, it's not very useful by itself. It's time for a major upgrade. We need to turn this iron into steel. So what's the big difference here? Well, it all boils down to one thing: carbon content. Pig iron is just saturated with carbon from the furnace. We're talking around 4%. That makes it hard, yeah, but also incredibly brittle, like it'll shatter. Steel, on the other hand, is simply iron where we very carefully lowered and controlled that carbon content. That's what makes it so immensely strong and versatile. Okay, so how do we get rid of all that extra carbon? Well, one of the most famous ways is the Bessemer process. You pour the molten pig iron into this huge pear-shaped container called a converter, and then you blast pure oxygen straight through it. The oxygen sets off this incredibly violent reaction, burning off the excess carbon as carbon dioxide gas, and other impurities form another layer of slag. It's fiery, it's dramatic, and it is a super effective way to turn brittle iron into amazing steel. So we've created this strong, shiny steel. It builds our cities, our cars, everything. But nature always wants to reclaim its own. All of that energy we just poured in to rip oxygen away from iron can be undone. See, iron has this natural tendency to go back to its original oxidized state. It's time to talk about rust. It's a really good question, right? If steel is so tough, why does it just fall apart? We put all this energy in to get the oxygen out, so why does it want to go back? Well, the answer isn't just simple oxidation. It's actually electrochemistry. Rusting is basically a tiny, unwanted battery playing out all over the surface of the metal. This table really breaks it down. Anywhere a single drop of water sits on a piece of iron, a little electrochemical cell can form. At one spot, which we call the anode, the iron itself actually oxidizes. That means it dissolves and gives up its electrons. Those electrons then travel through the metal to another spot, the cathode, where they allow oxygen from the air to be reduced in the water. These two separate reactions then combine, and those dissolved iron ions react more to form that flaky, reddish-brown stuff we all know as rust. And that was the entire life cycle. Wow. Okay, now let's finish up with a super fast review. If you remember absolutely nothing else for your exam, please remember these 5 key principles. Pencils ready? Let's do this. Number 1, the hero of the blast furnace is carbon monoxide gas, CO, not solid carbon. Number 2, limestone is the flux that gets rid of sandy impurities by making slag. Number 3, the huge difference between brittle iron and strong steel, it's all about the percentage of carbon. Number 4, rusting isn't just one thing, it's an electrochemical cell with an anode and a cathode. And finally, number 5, the final product of rust is usually a compound with the more stable iron 3+ ion. Got it? So there you have it, the epic story of iron. It's this constant cycle, right? We take a stable compound from the earth, pour in a massive amount of energy to make a useful but unstable metal, and then we spend all our time fighting to stop it from going right back to where it started. And that kind of leaves us with one final thought. As we get smarter and invent new alloys, can we ever really win the war against rust? Or is its victory in the end just inevitable? Good luck with your exams.